Hello everyone, today we will derive the Lagrangian equation from the Alembert principle. As you know that Alembert principle for a system of n particles is defined as sigma I is from 1 to capital N Fi minus Pi dot into delta Ri is equal to 0. Let us say it is equation number 1. Here Fi is the force acting on ith particle, Pi dot it is reverse effective force, and delta Ri is the virtual displacement of the ith particle. Now the position vector for the ith particle can be written as in terms of the generalized coordinates as Ri is equal to Ri q1 q2 q3 qk qn t, and this is equation number 2. Here q1 q2 q3 qk qn, these are the generalized coordinates, and t is a time. Now if we differentiate equation number 2 with respect to time, then we will have dri over dt is equal to Ri dot, we can write Vi equal to del Ri over del Q1 dQ1 over dt plus del Ri over del Q2 dQ2 over dt plus del Ri over del Qk dQk over dt plus del Ri over del Qn dQn over dt plus del Ri over del t. Let us say it is equation number 3rd. Now equation number 3rd can be written as dri over dt. You know that it is equal to Vi, or you can write it as Ri dot. It will be sigma k is from 1 to small n del Ri over del Qk into Qk dot. You know that Qk dot is equal to dQk over dt plus del Ri over del t. Here Qk dot are the generalized velocities term. So here now virtual displacement can be written as delta Ri is equal to del Ri over del Q1 into delta Q1 plus del Ri over del Q2 into delta Q2 plus del Ri over del Qk into delta Qk plus del Ri over del Qn into delta Qn. Here time is not taken because in virtual displacement time is taken as constant, so del Ri over del t term will be 0. So delta Ri is equal to sigma k is from 1 to small n del Ri over del Qk into delta Qk. Let us say it is equation number 5. Now we again write the D'Alembert principle, and that is sigma I is from 1 to capital N Fi minus Pi dot into delta Ri. Now if we see this principle, then we have here two terms. One is Fi into delta Ri and other is Pi dot into delta Ri. So we will write these two terms and find the Lagrangian equation. First I write the first term, that is sigma I is from 1 to capital N Fi into delta Ri. So it can be written as sigma I is from 1 to capital N Fi into sigma k is from 1 to small n del Ri over del Qk into delta Qk. This is the term for the virtual displacement of the ith particle. We can arrange this term as sigma k is from 1 to small n, sigma I is from 1 to capital N Fi into del Ri over del Qk into delta Qk, because we write here first k is from 1 to small n, because a particular particle can have either one generalized coordinate or more than one generalized coordinate. Suppose the ith particle has 3 generalized coordinates, and those are q1, q2 and q3. So your term will be like Fi dot del Ri over del Q1 into delta Q1 plus Fi into del Ri over del Q2 into delta Q2 plus Fi into delta Ri over delta Q3 into delta Q3. So we can write here the term sigma k is from 1 to small n and sigma I is from 1 to capital N Fi into del Ri over del Qk into delta Qk. Now we can write this term as sigma k is from 1 to small n Gk into delta Qk. Here Gk is equal to sigma I is from 1 to capital N Fi into del Ri over del Qk, right? So we can write it as sigma I is from 1 to capital N Fi. We can write it as Fxi. It is the x component of the force of ith particle into unit vector I, Fyi unit vector j, F plus Fzi unit vector k into del Ri over del Qk. Ri is like your xi unit vector I plus yi unit vector j plus zi unit vector k. So this term will be I del xi over del Qk plus unit vector j del yi over del Qk plus unit vector k del zi over del Qk. You also know that I dot I, j dot j, k dot k is 1 and I dot j, j dot k, k dot I is equal to 0. Here I, j, k are the unit vectors. So this term finally becomes Gk is equal to sigma I is from 1 to capital N, I dot I is equal to 1 Fxi into del xi over del Qk plus Fyi del yi over del Qk plus Fzi del zi over del Qk. Let us say it is equation number 7. Here Gk is called as the generalized force. If you see equation number 6, then this will give you a dimension of the work, but it is not necessary always that delta Qk represent the length and Gk represent the force. In some cases they may have the different physical quantities, but it is important that the product of Gk delta Qk will always be the dimension of the work. For example, delta Qk, it is a generalized coordinate and it is represented in angle, then Gk will have the dimension of torque, right? Because angle can be represented in radian. So work has the dimension of force into displacement, means Newton meter. So here Gk will represent the torque. Torque has force into perpendicular distance, so it will have the same dimension as the work. Now we will define the second term, sigma I is from 1 to n pi dot into delta Ri. You know that pi is the it is the linear momentum and it is equal to mi Ri dot. So pi dot will be equal to mi Ri dot. Mi here is mass for a particular particle. Here ith particle we have considered and it is not varying. So it will be this term sigma I is from 1 to capital N pi dot into delta Ri can be written as sigma I is from 1 to capital N mi Ri double dot into sigma delta Ri. You know that it is equal to sigma k is from 1 to small n del Ri over del Qk into delta Qk. Again we will write sigma k is from 1 to small n first, and then sigma I is from 1 to capital N, mi ri double dot into del ri over del qk into delta qk. Now we can write this term sigma I is from 1 to capital N mi ri dot into del ri over del qk as equation number 9. How we can write this term as equation number 9? Let us differentiate the term mi ri dot into del ri over del qk with respect to time. So to find the value of this term, we will start from here, this term, and it is d over dt mi ri dot into del ri over del qk. Now if I differentiate this, then you see that it will give you the differentiation of first, it will be mi ri dot, and the second as it is. So this is the term. Then I will write the first term as it is. So our first term is mi ri dot and the differentiation of second, so it will be d over dt del ri over del qk. Now because it will be here in plus, so when we write this in right side, then it will become minus. Means if we find the value of this term, then it will be like sigma I is from 1 to capital N mi ri double dot del ri over del qk plus mi ri dot into d over dt del ri over del qk. Then we can find the value of sigma I is from 1 to capital N mi ri double dot into del ri over del qk, and this will be equal to sigma I is from 1 to capital N d over dt mi ri dot into del ri over del qk. So let us say it is equation number 9. Now one thing also you have to remember here, that the dot cancellation law, and you know that the dot cancellation law is del ri over del qk is equal to it is equal to del ri dot over del qk dot. So del ri dot, it is you can write it as del vi over del qk dot. Let us say it is equation number 10. Now we will write the value of del ri over del qk is equal to del vi over del qk dot in equation number 9. So our term sigma I is from 1 to n mi ri dot double dot mi ri double dot into del ri over del qk becomes sigma I is from 1 to capital N d over dt mi ri dot can be written as vi, and del ri over del qk can be written as del vi over del qk dot minus mi ri dot can be written as mi vi into del ri dot over del qk, it can be written as del vi over del qk, right? So if we use equation 8, then we can write sigma I is from 1 to capital N pi dot into delta ri, and it becomes sigma k is from 1 to small n sigma I is from 1 to capital N d over dt mi vi dot del vi over del qk dot minus mi vi into del vi over del qk into delta qk. Now this equation can be written as like sigma k is from 1 to small m d over dt del over del q k dot sigma I is from 1 to m 1 by 2 mi vi dot vi minus del over del q k sigma I is from 1 to capital N 1 by 2 mi vi dot vi into del q k. Right, how we can write this term d over dt mi vi dot del vi over del q k dot as this term. Let us start to find the value of this term mi vi dot del vi over del q k dot. Now how I can find this value? Let us start del over del q k dot vi dot vi. Now this will be equal to first as it is the differentiation of second with respect to q k dot, so it will be del vi over del q k dot plus the differentiation of the first, it will be del vi over del q k dot into vi, so it will be twice vi dot del vi over del q k dot. Now if I find the value of vi dot del vi over del q k dot, then it will be here 2 will be in denominator on the left side, so it will be 1 by 2 del over del q k dot vi dot vi. I can also write it as del over del q k dot 1 by 2 vi dot vi, because mi is constant for a particular article, so we can also introduce it, and the term mi vi dot del vi over del q k can be written as equal to this term here. It will be del over del q k dot sigma I is from 1 to capital N 1 by 2 mi vi dot vi. Similarly for this term mi vi dot del vi over del q k, you can write it as del over del q k sigma I is from 1 to capital N 1 by 2 mi vi dot vi into delta q k. Now we know that v dot v is equal to v square, so we can write it as sigma k is from 1 to small n d over dt, and this term is the total kinetic energy of the system, so it will be del t over del q k dot minus del t over del q k into delta q k. Here t is kinetic energy. Let us say it is equation number 12. Now putting the value of sigma I fi dot del ri from equation 6 and sigma I pi dot into delta ri from equation 12 in D'Alembert principle, because in D'Alembert principle you know that there were two terms. One was sigma I fi into delta ri, and the second was sigma I pi dot into delta ri, right? So we write here when we use these two equations, then your equations becomes sigma k is from 1 to small n d over dt del t over del q k dot minus del t over del q k minus gk into delta q k is equal to 0. Let us say it is equation number 13. We have put these two equations 6 and 12 in D'Alembert principle. Now for holonomic constants, you can note write delta q k is equal to 0, so delta q k cannot be 0. That means your this term will be 0. So when we put this term equal to 0, then we find gk is equal to d over dt del t over del q k dot minus del t over del q k. This is a very important relation, and it is called as the general form of the Lagrangian equation. Here Gk is the generalized force, capital T is the kinetic energy, Qk dot is the generalized velocity, and Qk is the generalized coordinate. Now for a conservative system, we know that force can be written as the gradient of the scalar function, and that is potential energy in terms of the negative sign. So Fi can be written as minus del I V. Here del I is the D'Alembert operator, and it is equal to I del over del x plus j del over del y plus k del over del z. Here I, j, k are the unit vectors, and del over del x, del over del y, del over del z are the partial derivatives along x, y and z axis. You know that force can also be written as Fi is equal to Fxi unit vector I plus Fyi unit vector j plus Fzi unit vector k. Fxi here is the scalar component of the force along the x-axis. Similarly, Fyi is the scalar component of the force along y-axis of ith particle, and Fzi is the scalar component of the force along the z-axis of the ith particle. Here I, j, k are unit vectors. So if you write here Fi like here Fxi plus Fyij plus Fzik, then you see that your Fxi here will be minus del V over del xi. Similarly, Fyi will be equal to minus del V over del yi, and Fzi will be equal to minus del V over del zi. Here V is potential energy and it is not a vector quantity. So from equation 7 we can introduce the scalar component of the force in terms of the potential energy, and then it will be equal to Gk is equal to minus sigma I is from 1 to capital N. Here your term was Fxi, so I will write here minus del V over del xi. In all the terms there will be minus, so I have already taken it out. So it will be minus sigma I is from 1 to capital N del V over del xi into del xi over del qk plus del V over del yi over del qk plus del V over del zi into del zi over del qk. Let us say it is equation number 16. So we can write it as minus del V over del qk, because V is a function of xi, yi and zi coordinates, and it is equation number 17. So here generalized force has been described in terms of the potential energy, and earlier in equation 14 generalized force has been described in terms of the kinetic energy, right? So if you see here from equation number 14 we can write as Gk is equal to minus del V over del qk. So it becomes your equation number 18. Your equation number 14 becomes equation number 18 in the form like. As you know that for a conservative force you always know that potential energy is a function of the position coordinates. It is not a function of the velocity or generalized velocity. Similarly here V is a function of only the generalized coordinates. Here V is not a function of the generalized velocities. So when it is not a function of the generalized velocity, so we can write our term del V over del qk dot equal to 0, and let us say it is equation number 19. Now we can arrange our equation 18 as d over dt del t over del qk dot. Now you know that del V over del qk dot is equal to 0. So if you subtract 0 from del t over del qk dot, then it will not affect the result. So we can write it as del V over del qk dot. This is equal to 0 minus del over del qk t minus v is equal to 0. Let us say it is equation number 20. Now we introduce a new function that is called as the Lagrangian function. and it is denoted by capital L and is equal to T minus V. Here T is kinetic energy, V is potential energy, and L is Lagrangian. So your equation 20 takes the form d over dt del L over del q k dot minus del L over del q k equal to 0. Here k can be 1, 2, 3 up to n. It will depend upon the number of the generalized coordinates. If the number of the generalized coordinates is small n, then you see that there will be n number of the Lagrangian equations, right? So this is a very important form, and this Lagrangian equation will be used in solving the classical dynamics problems, and you will see that the classical dynamics problems by using these equations can be easily solved. Thank you.